Hi, my name is Taewook and I'll present Int3DNet, a sim motion cross-attention network for 3D intention prediction in mixed reality. In this paper, we aim to predict where a user will interact in 3D space before they actually touch the object. In mixed reality, many systems processes start after contact. So the user reaches for an object, and the system recognizes the target object, and then reasoning happens, then system action is triggered. Such delays are especially critical in MI systems, where even minor latencies can disrupt immersion. But what if the system could anticipate the target object before contact? If we can predict where interaction will happen 500 to 1500 milliseconds earlier, the system can start processing in advance. The system can provide real-time feedback with minimal latency, significantly enhancing the user experience. To this end, we propose an intention prediction network, Int3DNet, tailored for proactive system in ML environments. We make three main contributions. First, we propose a sim motion cross-attention network that predicts a 3D intention heat map directly over a sim point cloud without explicit object segmentation. Second, we validate robustness across simple and cluttered sim using MoGaze and CIRCLE dataset. Third, we demonstrate intention-based VQA as practical use case, where we crop the predicted intention area and feed it to a visual language model. It's the problem definition. We focus on signals that are commonly accessible in MR. A sim-point cloud is available from an IGBT sensor. Head and hand trajectories are also relatively easy to obtain from commercial HMDs. We also use a head orientation as a proxy for attention, since gaze signals are not always available on HMDs. Given those inputs, our model outputs a per-point intention heat map over the 3D scene. So instead of predicting an object level, we predict where the interaction will happen in 3D space. Now I will explain about the architecture of Int3DNet. First, we encoded the scene point cloud with a PointNet++ to get per-point scene features. This gives us a dense feature vectors for every scene point. For encoding human motion, we only use the path trajectories of the head and both hands. We apply a discrete cosine transform to reduce temporal redundancy and then encode them with a spatial temporal GCN. And past head orientations are also encoded with DCT MLP modules and fused with the motion features using the STGCN. With the encoded scene and motion features, we condition the scene directly on motion using cross-attention. Scene features act as queries, while motion features serve as keys and values, producing motion-aware features for each scene point. We then fuse these features and use an MLP head to predict a per-point intention score. For training, we use composite, loss, weighted BCE, focal, and dice, since intention regions are sparse and imbalanced. Each term helps handle class imbalance, hard examples, and region-level consistency. We conducted experiments on two datasets, CIRCLE and MoGaze. The MoGaze dataset is a collection of human motion data for pick and place tasks in an indoor environment. It contains relatively simple scenes where goal objects are easily visible. In contrast, the CIRCLE dataset includes cluttered scenes with partially or fully occluded goal positions, because both open and cluttered scenes naturally occur in real-world environment. We evaluate on both datasets. Baselines, we tested whether simpler cues are already enough for 3D intention prediction. Head orientation assumes users interact with what they look at. Head plus scene as scene geometry for spatial context. Motion forecast predicts future hand trajectories and infers intention from the predicted wrist position. Only scene relies purely on scene appearance without any human cues. For oblations, we analyzed what makes our model effective, replacing cross-attention with simple MLP fusion, reversing the attention direction, and comparing different loss functions, including BCE, focal, dice, and their combination. For evaluation, we use heat map and region metrics. Similarity for distribution overlap, AUC for ranking, and mean IOU dice for spatial overlap. On the circle dataset, Int3DNet constantly outperforms our baseline across horizons up to 1500 milliseconds. In contrast, other baselines show unstable or degraded in performance. In particular, the motion forecast baseline is highly sensitive to the sampling time, showing substantial degradation as the sampling point shift. On the MoGaze dataset, Int3DNet outperforms our baseline up to 1200 milliseconds. But beyond that, performance becomes comparable to other baselines. This is mainly due to characteristics of MoGaze, and I'll come back to this in the discussion. Here are sample prediction results on the circle dataset. The red area represents intention region, the left figure shows the ground truth intention area, and the right shows our prediction alongside human motion. You can see that our predicted intention area stays well localized around the ground truth region. Here are our sample prediction results on the MoGaze dataset. Similarly, our predicted intention area stays localized around the ground truth region. To further showcase its potential, we also built an intention-based visual question answering pipeline using the ARIA digital twin dataset. We reconstruct the scene point cloud from IGBD, run Int3DNet to predict the 3D intention area, then project that area back to the image plane and crop the relevant region for a vision language model. Here we present demonstration result on the ARIA digital twin dataset. As you can see, the user's target object. These results confirm both the real-world applicability and the generalization capability of our method. If we feed the full image into VLM, it tends to produce many irrelevant object candidates. In contrast, intention-based cropping produces a much smaller candidate set, and it reduces visual token usage by about 93.6%. This directly improves efficiency for on-device or latency-sensitive MR systems. Here, I summarize what our results actually validate. First, the model is robust across time horizons from 500 to 1500 milliseconds before interaction. On the circle dataset, which contains cluttered and complex scenes, Int3DNet consistently outperforms all baselines across horizons. On MoGaze, performance remains strong up to about 1200 milliseconds, and then gradually degrades. This is mainly due to dataset characteristics. In MoGaze, the motion often has not fully committed to a specific target in early time windows, so the intention is inherently ambiguous. As you can see in the image on the right, even 1500 milliseconds before an interaction, the motion often does not commit to a target. And we also discussed about the effectiveness of sparse human motion cues. When we use only scene geometry for intention prediction, the results are stable over time, but the overall accuracy is lower. It performs relatively better on MoGaze when scenes are sampled, but its performance drops on circle, which contains cluttered and complex environments. This suggests that using scene geometry alone without human cues is not sufficient for accurately anticipating human intention. From the comparison between the head plus scene baseline and Int3DNet, we can see that combining motion and attention cues significantly improves performance. This highlights the effectiveness of incorporating sparse human motion cues for intention prediction. To sum up, Int3DNet predicts where interaction will happen in 3D space by fusing sparse head-hand motion with scene geometry through cross-attention, and it generalizes across both simple and cluttered scenes. We believe our method can play a vital role in improving the efficiency of real-time MI systems. while also providing insights into building motion, human attention, and scene geometry for future intention research. Thank you.